Welcome to this third lecture in EE404. In the last lecture, we have seen the different representations for nonlinear systems, and I told you that we're going to use almost always a state space representation for nonlinear systems. So now we are ready to see the types of different nonlinear state space representations. So depending on whether the function f and g, which variables they are dependent on, we call nonlinear systems in different ways. So let us now write types of nonlinear systems. So the first type that we are going to see is that a time-varying nonlinear system. X dot is equal to f of t, x, and u, and y is equal to g of t, x, u here. Okay, so we almost always specify an initial condition for the system. This is the most general form. And we are almost never going to use this, right? So this is a time-varying nonlinear system. So why is it time-varying? So sometimes students actually are confused about the concept of time-varying and time invariance. So in this case, of course, the signals x, y, and u, they are functions of time. But this is not related to the concept of time invariance and time varyingness. Okay? So here, the relationship between x, u, and the relationship between x, u, and y they are changing with respect to time. So this explicit time dependence is what is important for time invariance or time varyingness. Okay? So here, when I write a system like this, x dot is equal to, when I write x squared, this is a nonlinear system, and it is a time invariant system. Why is that? Because this relationship, let me write here also u, relationship between u and x is time invariant. The relationship, the differential equation never changes with respect to time. So this is time invariant nonlinear system. On the other hand, if there is an explicit t dependence, t times x squared plus u. Remember that in this case, if I write the first differential equation here, I can write it like this: x dot of t, I can put t dependencies here, x of t squared plus u of t. So these are all functions of time, and they change with respect to time. Okay? But the relationship between u and x, or when I remove u from these equations, the relationship of x dot and x is invariant with respect to time. This differential equation does not explicitly depend on time, although the signals are dependent on time. Okay? So this is a time invariant system, irrespective of the fact that these signals are they are functions of time. Okay? On the other hand, this second differential equation, you see that in this case there is an explicit time dependence of the differential equation on time. So at time t is equal to 1, this differential equation is satisfied. At time t is equal to 2, this differential equation is satisfied. These are definitely different differential equations. So the differential equation describing x and u is changing with respect to time in that case. Okay? That is why such a system would be a time-varying nonlinear system. Okay? So here, the right-hand side is a function of x and u, and it is not an explicit function of time anymore. Okay? So x and u are functions of time, but x dot is only a function of x and u. So the right-hand side is a function of time only through x and u here. Okay? There is no explicit dependence on time. That is what we call a time-invariant nonlinear system. On the other hand, if I write this right-hand side, here, this is not only x and u, because when I give you x, when I give you u, there is still an explicit time dependence here on the right-hand side. Okay? That is why the right-hand side here should be a function of t, x, and u. There is an explicit dependence of the differential equation on time here in the second case. As a result, the second system is time varying. The first system is time invariant. All right? So this is the most general case that you can see. The system is both time varying, and furthermore there is an input in the system. The second case is going to be the case when the right-hand side is not a function of u anymore. Y is equal to g of tx. Okay? In this case, there is no explicitly defined input on the system that you can use for control. So this concept, the existence of input or its non-existence, is called forced or unforced system. So this is called, when there is an input dependence on the right-hand side, the system is called a forced system. Okay? Meaning that there is an input that you can change the behavior of this system by changing the input. It is a forced system, and in this case, when there is no input in the system equations, this is called an unforced system, unforced nonlinear system. What about the time invariance here in the second case? The system is definitely not time invariant, it's time varying because of the explicit dependence on time. Time varying system. Okay? This was the second case of systems, and the third case is going to be the time invariant case. X dot is equal to f of xu and y is equal to g of xu. Okay? In this case, we see that there is no explicit time dependence of the on the function in the functions here. So that means that this system is a time invariant system, time invariant nonlinear system. And in this case, you see that there is an explicit dependence on the input as well. There is an input in that system. That means that this system is a forced system. Okay? So sometimes, especially physics people or mathematics people, people in these sciences, they call time invariant as a stationary system. Okay? It means the same thing. The relationship between the variables does not change with respect to time. And the last case that we can talk, probably, which is the one that we're going to use the most, is a system of this type. X dot is equal to f of x, and y is equal to g of x. This system does not depend on any input, or you see that there is no explicit dependence on time either. That means that this system is time invariant, and it is unforced. Okay? There is a specific name given to such systems in the control literature, and these are called, when both of these properties exist in a system, we call that system an autonomous system. Okay? It is an autonomous nonlinear system in this case. So of course there might be convergence between such systems. And now I'm going to write an important case. If you take a time invariant system, which is described like this, and if you set the input u of t to a constant, if you set the input u of t to a constant, then that system becomes actually an autonomous system from that point on. Okay? If you set the input u to a constant, then you remove the u dependence from the system. And in that case, you can actually turn such a system into an autonomous system of that type by using always a constant input. Okay? And that is going to be a remark that we are going to write here because it's going to be useful later for us. Remark. Suppose that we have a time invariant nonlinear system. X dot is equal to f of xu and y is equal to g of xu. Okay? If we set u of t is equal to ue, this notation u sub e is going to get a meaning in the next part of the course. It's going to be u equilibrium actually, but we are not ready for calling it like this yet. So this is constant input. So this is for all t. Okay? If we agree that if we set u of t to a constant for all time, that means constant input, then the system can be treated as an autonomous system. Why is that? Because x dot is equal to f of x. Instead of u, if I substitute a constant, ue, then this only becomes a function of x. This function now becomes only a function of x. Similarly, y is equal to g of x ue. So then this new function, I can actually define it as f1 of x, and I can define this function as g1 of x. Then I would have an autonomous system given like x dot is equal to f1 of x and y is equal to g1 of x. This is nothing but an autonomous system now. So I can give you an example for you to be able to imagine what is happening here. So x dot is equal to, let us say that it is x plus, let us use this example again, x plus u times x. Let us say that this is given like this, and y is equal to e to the x times u. Let us say that this is my original nonlinear system. Then suppose that I take the input u of t to be a constant. This is definitely like f of xu, and this is like g of xu. Okay? Let us say that I take u of t is equal to 2. Okay? A constant. In that case, x dot becomes x squared plus 2x, and y becomes 2e to the x. Okay? So you see that the right-hand sides are now constant. They are not dependent on u anymore. They are only dependent on x, and this is the form of an autonomous system. Okay? So this is my f1 of x, and this is my g1 of x. Okay? So we can treat time invariant systems as autonomous systems if we set the input to a constant for all of the operation of the system. Okay? So we can turn such a system into such a system by taking the input as a constant. So now we have defined types of nonlinear systems. So it would be a nice exercise now to think about linear systems. what would be their different types, how they would look like. Okay? So now, let me try to show you how actually linear systems in state space form would look like with these different forms. So let us try to write the most general system. So I would have linear system. Let us say that it is time varying. Okay? And let us say that it is a forced system. So there is an input in this system. In this case, how would the linear state space representation look like? In that case, I would have, so remember, this is how a time invariant linear system would look like. Okay? So this is time invariant forced linear system. Our classical state space system in the course EE404. So it is forced, there is input on the right hand side, it is linear, and how can I make this system time varying? So remember, when I try to make this system time varying, I need to keep its linearity. Okay? So really, I cannot actually put some arbitrary terms here to make this system time varying. So what do I call this representation? Sometimes this representation is shown as this. If I am given ABCD, I can write this representation. So, and this ABCD describe the relationship, all of the relationships between these variables. Okay? So if a linear system is time varying, then this representation matrices would be time varying. What does it mean? They would depend on time. So if I want to write a time varying linear system, then this A matrix would be dependent on time. B can depend on time, and Y, C can depend on time, and D can depend on time. Okay? So this is how a linear time varying forced system would look like. So the ABCD matrices are dependent on time. If they are dependent on time, then the system becomes time varying. So now let us look at a linear system. Let us say that it is time varying, and suppose that it is unforced. Okay? In this case, how would the representation look like? Unforced, so linear and time varying parts are okay here in this representation. In order to be able to make the system unforced, I should not include any input term. Okay? So that would be a system in the following form. A linear time varying and unforced system. There is no input, as you see in that representation. And linear, time invariant, and finally a forced system would be just this. X dot is equal to AX plus BU, Y is equal to CX plus DU. The representation is not changing with respect to time. A, B, C, D are not changing with respect to time, and the system has an input term that can be used to force the system into some behavior. And finally, I have linear, time invariant, and unforced system. What does this mean? This means I want a linear system and autonomous system. Remember, these two properties means autonomous. Okay, linear autonomous system. How would it look like? In that case, I would remove the input term from this one as well. X dot is equal to AX, and Y is equal to CX. So if a system doesn't have any input, so is it always going to give me zero response? If a system doesn't have any input, then do you think its response is always going to be zero? Obviously not. Then autonomous systems would be useless in that case. So here, a system can give responses to two factors. One is the input, the other one is the initial condition. So an unforced system still might have a non-zero response due to initial conditions. Okay? So in such cases, we don't think about the input at all, but we will think about different initial conditions of the system. Okay? So this actually completes the different types of nonlinear systems. Sorry, I have erased that. Now we can actually go into the part related to the so-called equilibrium points, which is probably the most important concept in nonlinear control and the analysis of nonlinear systems. So first, in order to be able to understand the concept of an equilibrium point, we are first going to think about only the autonomous systems. And then we are going to try to generalize that idea to time-invariant systems as well. So we are not going to cover time-varying systems at all. You would have to make that generalization yourself in your mind. So here, let us say equilibrium points for autonomous systems. Let's write the definition. Consider an autonomous nonlinear system. X dot is equal to f of x. A vector, so this is an nth, if this is an nth order nonlinear system, then X has n components. So a vector in the state space, of course, xc in Rn, okay, is called an equilibrium point. Sometimes people in different areas of studies would call an equilibrium point with different names. So mathematics people would call an equilibrium point a singular point. Okay? Physics people would sometimes call an equilibrium point as a stationary point, and they can sometimes use the name of fixed point for the equilibrium point. But they would all denote the same concept. A vector xc in Rn is called an equilibrium point if and only if, this is my definition, f of xe is equal to 0. Okay? So if the right-hand side is equal to 0 at that point, then we call that point as the equilibrium point of this system. All right? So now we're going to try to understand what an equilibrium point is. The first thing that I would like to do here to explain to you what an equilibrium point is to consider a scalar system. Okay? X dot is equal to f of x. Let us say that x is an element of the set of real numbers. Okay? So in this case, we have a first order nonlinear system when x is scalar. So this is my state space. The real line is my state space. Any point on this line is a state vector if you want. So I can actually show f on this state space. Okay, f is a function of the state. So I can actually show this state function, nonlinear function, f of x, like this. Okay? It is defined on the state space. So now I would like to understand the behavior of this nonlinear system in the state space when I start that system at different points on the state space. So when I choose different initial conditions for this system, what happens to the state? So suppose that I start this system somewhere here at this point. Okay? At this point, you see that f of x is positive. So this is my initial condition x0, and at x0, f is positive. What does it mean? So in this differential equation, I have x dot is equal to f of x. What is x dot? X dot is the rate of change of x. Okay? So if I start the system here, since f of x is positive at this point, x dot is going to be positive, which means that x is going to increase. If the time derivative of x is positive, that means x is going to increase. And time derivative, if it is negative, then the x is going to decrease. So what does it mean? So it means that when I start this system somewhere here, then x is going to go towards right. Okay? So it's going to go towards right. So we are going to land in a point to the right of this initial point. Okay? But f is still positive at that point, so we're going to move even further to right. But you see that here, the value of x is changing here. Sorry, value of f of x is changing at these points. What does a change in f of x means? The velocity of x would decrease when the system takes the state from here to here. The velocity is always decreasing when I'm going towards right at these points. Okay? So x is getting slower and slower as it approaches to this point at which f of x is equal to 0. Okay? What happens at this point? Because of this definition, this is an equilibrium point. Okay? xe. I will call this system has let me say that f is something like this and f continues like this. You see that f intersects the 0, the value 0 only at 2 points. So these 2 points are equilibrium points of the system. So what is going to happen when x reaches this point? When it reaches this point, what is going to happen? F of xe is going to be equal to 0, and that means that x dot is going to be 0. When x dot is equal to 0, what does it mean for the motion of x? It means that x is going to be a constant. It is not going to change with respect to time. So when the system reaches here to this equilibrium point, it is always going to remain there. When x is there, or when I start the system exactly at this equilibrium point, the state will always stay at the same point. Okay? That is a very, very important property. It is actually the defining property of an equilibrium point. Okay? So what about this point? This point has the same property. Okay? So, but you see what is happening to this state of this system. When I start it here, somewhere here, it is actually going, the state is going towards right, and it's converging to this point. What about if I start a system? What if I start a system somewhere here? In that case, I see that f of x is negative at that state point. Okay? So that means that x is going to decrease. So x is going to go in that direction. All right? So similarly, we are going to land into a point somewhere here, and then the f of x is still negative. We are going to continue going towards left, and we are going to continue until we converge to this equilibrium point. Okay? And once we converge to that equilibrium point, then the system remains there. The state remains exactly at that equilibrium point, and it never leaves. So what about the case when I start the system here? Okay? In that case, you see that the system f of x actually is positive. That means that the state is going to move towards right. It is going to increase. All right? So if I start the system somewhere here, the state is going to move away from the equilibrium point. Okay? And if I start the system somewhere here, x is going to be decreasing. So since f of x is negative here, so the states would be moving towards left. So you see that, but what if I start the system exactly on this equilibrium point? In that case, you know that since f of x is equal to 0, the x is going to remain where it is. All right? So for both of the equilibrium points, we had a similar behavior if we start the system exactly on the equilibrium points. Okay? If we start the system exactly on the equilibrium points, the states will remain where they started. Okay? But you see that the behavior around the equilibrium points is quite different for this system. Okay? For the first equilibrium point, the states around the initial conditions around the equilibrium point would result in a convergence to the equilibrium point. Okay? On the other hand, for states around this equilibrium point, for initial states around this equilibrium point, if I start the system somewhere very close but not exactly on the equilibrium point, I see that the states will diverge away from this equilibrium point. Okay? So this is a very, very classical example of nonlinear stability of equilibrium points. This equilibrium point and this equilibrium point, they satisfy the same equation, but their stability characteristics are different. When we investigate the stability of nonlinear systems, we are going to look at the equilibrium points and try to understand whether those equilibrium points are stable equilibrium points or unstable equilibrium points. We are going to call the first type of equilibrium points as stable equilibrium points, and the second type of equilibrium points as unstable equilibrium points. But there is really a lot of time until we come to that point. Okay? But here we see the important characteristics of an equilibrium point. When we start the system at an equilibrium point, the state will never change its position anymore. So what about a second order system? So I define x1 dot x2 dot. This is my x dot. I have f1 of x1 x2, f2 of x1 x2. This is my f of x. This is my f of x. Okay? An autonomous system. A second order autonomous system. Okay? In this case, my state space is not only a line. Okay? When the system is first order, the state space is just a real line. On the other hand, when the system is second order, our state space is going to be a plane. Okay? x1, x2 plane in this case. So this is my state, I'm sorry. So I would have x1 and x2 plane as my state space. Okay? Then how can I visualize the motion of the states due to this system dynamics there? So suppose that I start the system here. All right? Then what is x dot? X dot is the rate of change of the vector x. Okay? x1 dot is the rate of change of the x1 component, and x2 dot is the rate of change of the x2 component. Okay? So when I look at what f of x is, so this is my x1 0. So let us say this is x1 0 and this is x2 0. So let me say that these are initial conditions. Okay? how would the system move from that point? First of all, I would evaluate the function f on this point, x10, x20. Okay? This is going to give me a vector. The vector is going to be composed of elements f1 and f2. Okay? So suppose that that vector, when I evaluate this vector in x1 of 0 and x2 of 0, suppose that vector turned out to be 1, 0. Okay? So this is my f of x of 0, let us say. All right? So this is nothing but f1 of x10, x20, and f2 of x10, x20. So let me say that this value turned out to be 1 and this value turned out to be 0. Okay? In that case, how will the state move away from this point? I know that rate of change of x1 is going to be 1, so x1 is going to increase. On the other hand, x2 is going to try to remain constant because its rate of change is 0. Okay? So the state is going to move in this direction. Okay? So you see that this 1, 0 is nothing but the velocity vector of the state at a point on the state in the state space. Okay? So if these values, if they turned out to be 0, 1, then the state would move in that direction, upwards. Okay? If these values were 1 and 1, then we would move with a 45-degree angle to the x1 axis. Okay? So here we see something very, very important for the system. When I look at an equation like this, a nonlinear system equation like this, f of x is the velocity vector for x in the state space. So if we are at a point on the state space, if we evaluate f at that point, that is going to give us the velocity vector. In this case, this gave us 1, 0. Suppose that I moved here in this direction just a little bit, infinitesimally. Then I am going to evaluate these functions once more at the new point, and I am going to look at the velocity vector. Suppose that the velocity vector turned out in that direction. This is my f of x at this point. Then I'm going to move in that direction infinitesimally, and then I'm going to check what f is. And that is going to give me just another direction. The magnitude of f might be larger or smaller. That means the magnitude of the velocity. So how fast x is going to move in that direction. And the ratio of the elements of f of x would give you the direction of the velocity. Okay? So in that case, I would move in that direction. So in this manner, the system will have a trajectory in the state space. Okay? So here we understand that this f of x is nothing but the velocity of x on the trajectory of a system. Okay? So then what does it mean for the velocity to become 0? F of xc equals to 0. That definitely means that when I am at a point xe, even like this, suppose that this is my xe, then f of x is equal to 0 at that point. That means that the velocity of x is going to be 0 at that point. So there will be no motion from that point on anymore. Okay? So if I start the system at xc in the state space, the trajectory of the system will remain at that point from that time on. So now let us write this fact. That is the property of the equilibrium point, defining property of the equilibrium point. Remark. If at time t1 we have x of t, let us say x of t1 is equal to xe, so suppose that at time t1 we have the state value xe. At time t1 the state is here. Then I know the whole future trajectory of this system, because all of x of t's after that point will be equal to xc. Okay? Then x of t will remain at xe for all t larger than or equal to t1. Okay? So this means in verbal terms that the state vector remains at the equilibrium point xc forever. Okay? That is the property of an equilibrium point. When we start the system at an equilibrium point, or if the system state by itself reaches the equilibrium point at some time instant, then the state will remain there forever. So now we're going to see an example for which we are going to first derive the state space model, and then we are going to check its equilibrium points. So this example is a very, very common one, and I use this example really a lot. You will probably be bored at the end of the course of using this example over and over. But it is really an illustrative example, and it's easy to visualize what is happening with the equations. That's the reason that I use this a lot. So let us look at the example, which is the pendulum example. Okay? So suppose that we have a pivot point here, all right? And I have a massless rod here. So this is a massless rod. So it is just a stick without any mass. And suppose that there is a mass here, and the mass of this is the pendulum. So I will denote the vertical here like this, and I will define the angle theta here. Okay? The angle of the pendulum. I will denote this length with L. Okay? And suppose that I show the mass of the pendulum with M. Okay? I know that the pendulum actually is under gravity. Okay? So we have the gravitational force applied onto the pendulum, which is given as mg. Okay? So suppose that I have an electric motor here applying a torque to this pendulum. Okay? This torque is tau. We are not going to model the electric motor, so we are just going to assume that we are applying tau onto the pendulum. And suppose that there is a friction at the pivot point represented by the friction constant B. This is going to be viscous friction, the usual friction that we use in 302. Okay? Linear friction model. So here, this B is the friction constant at the pivot point. And here, tau is the input input torque. Okay? So I will define my system here as this. The input torque, tau is the input of the system, and theta is the output of the system. The angle of the pendulum is the output, and the torque applied by the electric motor is the input of the system. Okay? So I'm assuming that this mass is concentrated at a single point, so the inertia of this pendulum is ml square. Okay? I will not use this, but I'm assuming a point pendulum here. All of the mass is concentrated at a single point. So now let us first obtain the mathematical model of this pendulum. Everything is defined now. So the first thing that I'm going to do is to write J times, I would have theta double dot. Okay? I know that this is the inertia times the angular acceleration. This is going to be the net force applied onto the pendulum in the increasing theta direction. Okay? J times theta double dot is the net force, net torque applied onto the pendulum in the increasing theta direction. Okay? So I'm going to count the torques in the counterclockwise direction. Okay? A torque in the counterclockwise direction will be positive. A torque in the clockwise direction would be negative. Okay? So now let us try to write these torque terms. J theta double dot is equal to the first torque that is applied in the direction of increasing theta is tau. You see that tau and theta has the same direction. That means that I can here write first the input torque. Okay? Then I would write the torque related to the gravity here. All right? So I can actually put here this theta angle. All right? So I have theta here. And I can actually decompose this gravitational force into two parts. This part and this part. And which part do you think is going to cause a torque on the pendulum? We know that forces passing through the point of rotation does not cause any torque. Okay? So this part of the force will not cause any torque. On the other hand, this part is going to cause the torque. Okay? So here I am counting the torques in the increasing theta direction. Okay? But you see that this force is going to create a torque in the other direction, in clockwise direction. Okay? So that means that I'm going to put here a negative sign, and I will write this component of this gravity force here. It is mg times sine theta. Okay? And you see that immediately there is a nonlinear function here, sine theta, which would give us a nonlinear system. So when you look at this equation, do you think everything is correct so far? I still have the friction term that I didn't write, but do you think the things that I have written so far are correct? They are not correct because of this term here. This term is a force. Okay? Gravitational force is mg, and this mg times sine theta is the force which is perpendicular to the rotation here. But this is still a force. I need to convert it into a torque. What should I do? I need to multiply it with this length of the rod here. Okay? So this is going to be mgl times sine theta, which is going to give me a torque term. And this torque term is in the reverse direction. Okay? And the last thing that I need to do is to add the effect of the friction. So when theta dot is positive, okay? When theta dot is positive, that means that this pendulum is moving in that direction, towards the right. So it is rotating with, it is rotating in counterclockwise direction, okay? In that case, when theta dot is positive, what do you think the direction of the friction torque would be? There is a friction term here. When theta dot is positive, so this pendulum is moving like this, and then in which direction, clockwise or counterclockwise, would be the direction of the friction torque? We see that when the pendulum is moving like this, the friction torque will oppose this motion, okay? So when theta dot is positive, the friction torque should point in the reverse direction. That means that I need to have here a minus sign b times theta dot, okay? So when theta dot is positive, the torque direction is negative in the decreasing direction of theta. Okay? So this actually completes our mathematical modeling. Okay? So that is the main equation that we can use in order to be able to obtain the state space model of the pendulum system. All right? So now let us look at this. This is looking like the nonlinear differential equation that we have seen in the previous lecture. Now I can actually define my state variables and try to look at the equilibrium points of this system. The first thing that I'm going to do is to define a state variable, a state vector. And for defining a state vector, I need to know how many state vector elements or state variables would I use. So what is the order of this nonlinear differential equation? When you try to determine the order of a nonlinear differential equation, you need to look at the derivatives. What is the highest order of derivative that you see in this equation? Definitely it is 2. That means that this is a second order nonlinear differential equation. It is nonlinear. Why? Because of the sine function. This term is linear, but sine theta is a nonlinear term. Okay? A second order nonlinear differential equation means that my state vector should be composed of 2 elements. So I'm defining my state vector as x equals to x1 and x2, and I will define my x1 as the variable theta, and I will define the second state variable as theta dot. Okay? Just like the case of the differential equation state space conversion. So remember in the previous lecture, the output was y, and I defined my state vector y dot, y double dot, going until the y n minus first order derivative. Here n is equal to 2, so n minus 1 is 1, which means that in the state vector I have the first order derivative. The highest order derivative in the state vector is going to be n minus 1, and n is 2 here, so I have theta dot here. So now let me try to get the state equations. So the first thing that I'm going to do is to obtain x1 dot. x1 is theta, x1 dot is theta dot, which is the second state variable. Okay? That means that the first equation is going to be this. x1 dot is equal to x2. And the second equation is going to be related to x2 dot. x2 dot is the derivative of theta dot, which is theta double dot. And I can write theta double dot using this equation in terms of the input and the other state variables. So the first thing that I write is tau over j minus mgl over j. These are all constants in the system. And sine theta. Theta is x1, so I have here sine x1. Okay? And minus b over j. This j, remember, comes here when I try to express theta double dot. And and I would have, of course, theta dot. And we know that theta dot is nothing but x2, the second state variable. So I have my state space representation given like this. So this is the state space representation. So what is the type of this nonlinear system? Is it time varying? Is it forced or unforced? Is it autonomous? So when I look at these equations, I see that there is an input term. So this state space representation is definitely a forced state space representation. And we see that there is no explicit time dependence here. In any of these coefficients are constant. So it is a time invariant system. But no, we know that currently we only consider autonomous systems. Okay? So currently we define the equilibrium point only for autonomous systems. In that case, that means that here I need to get rid of the input term. So this torque term, in order to be able to convert this time invariant and forced system into an autonomous system, I need to take the input as a constant, tau. So let us say that the obvious selection would be tau is equal to 0. If I take tau is equal to 0, then this system is converted into an autonomous nonlinear system. So I have x1 dot is equal to x2, x2 dot is equal to minus mgl over j times sine x1 minus b over j times x2. Okay? So this is my nonlinear autonomous system. So now I can try to find the equilibrium point or equilibrium points of this system. Okay? What do? What I need to do is to equate the right-hand side of the equation x dot is equal to f of x to 0. Okay? But in this case, this f is also a vector. So this is f1 of x1, x2. The second element is f2 of x1, x2. Okay? So this is my f of x, and I need to equate this to 0, 0. Okay? That is the definition of the equilibrium point. And now I need to solve x1 and x2 values for which both of these equations are satisfied. Okay? Solve for x1 and x2 satisfying f1 of x1, x2 equals to 0, f2 of x1, x2 equals to 0. Okay? And they need to be satisfied at the same time. Okay? At the same time. Because if only one of them is 0, the state will still move in one of the directions. State will not remain at the same point forever. So now let us equate the right-hand side of these equations to 0. So the first equation that I get is x2 equals to 0. Remember, x2 was theta dot. So for an equilibrium point to exist, angular velocity of the pendulum should be equal to 0. Okay? That is our first equation. What about the second equation? It is this one. Minus mgl over j sine x1 minus b over j x2 is equal to 0. And I know that x2 is equal to 0 from the first equation. That means that this term is equal to 0. Suppose that mgl over j is non-zero. A pendulum is meaningless without the mass there. So suppose that everything here is non-zero. So what we need to have is sine x1 should be equal to 0. Okay? So these are the two equations that have to be satisfied. So when is sine x1 is equal to 0? I know that when x1 is equal to 0, it is 0. Or x1 can be pi. x2 can be, x1 can be 2 pi. So we know that sine is periodically equal to 0 with the period pi. So I know that any point which looks like x1 is equal to k times pi, and k is an integer, would be a candidate x1. Okay? So I would have the equilibrium points of the system can be characterized as follows. x2 is always going to be equal to 0. Angular velocity is always 0. And x1, angular position, has to be an integer multiple of k. Okay? K is an arbitrary integer. So if I draw my state space, so suppose that this is my state space, and I have x1, x2 here, where are my equilibrium points? If k is equal to 0, I have 0, 0 at this equilibrium point. This is the first equilibrium point. And if k is equal to 1 or minus 1, I would have these points. x2 is always 0 at an equilibrium point. So this is minus pi and pi here. And I would have minus 2 pi plus 2 pi here. So how many equilibrium points does this system have, do you think? How many equilibrium points does the pendulum system have? Obviously, when I look at this state space, I see that there are infinitely many equilibrium points. Okay, so I can write infinitely many equilibrium points. But now let us try to investigate the physical meaning of these equilibrium points. Okay? So we have already taken tau equals to 0. So there is no external torque applied on the pendulum. Let us now concentrate on this equilibrium at the origin. Equilibrium at the origin is this downward equilibrium of the pendulum. Okay? Theta is equal to 0. The first state variable k is equal to 0 there. And theta is equal to 0 and theta dot is equal to 0. Okay? So this equilibrium point is nothing but what happens when the angle theta is equal to 0 and the angular velocity is equal to 0. You know that if you leave the pendulum at its exactly downward point with 0 angle and 0 angular velocity, the pendulum will always be there. It will always remain there. Okay? Because there is no external torque applied onto the pendulum. And if I start the pendulum at this downward point, and then with 0 angular velocity, it would remain like this. That is the downward equilibrium point of the pendulum. There is just one more equilibrium point here, and there I would have the angle theta equals to pi 180 degrees, and the angular velocity is equal to 0. So the first equilibrium point that I have looked is xe1 is equal to 0, 0. This is the downward equilibrium point of the pendulum. The second equilibrium point that I would like to investigate is pi and 0. Okay? And what does it correspond to? When the angle theta is pi, the pendulum is looking at the ceiling. Okay? Directly looking at the ceiling. So it is the upward pendulum equilibrium in that case. If the pendulum is directly looking upward and if its angular velocity is 0, there is no external disturbance in the system, which means that the pendulum will remain at that vertical position forever. Okay? And that is our second equilibrium point. And this is the upward equilibrium point of the pendulum. What about the other ones? Minus pi and 0. Theta is positive in that direction. Negative direction would be that direction, and minus pi would be again when the pendulum is upward. Okay? So I would have again a similar equilibrium point to the second equilibrium point. What about 2 pi and 0? 2 pi and 0 would be a full rotation of the pendulum where the pendulum is pointing downwards again. Okay? So this 2 pi equilibrium point would be the same as the equilibrium point at the origin. So although mathematically the pendulum system has infinitely many equilibrium points, in physical terms or in physical interpretation, how many unique equilibrium points do we have? In physically, how many equilibrium points, how many unique equilibrium points do we have? We have only these two. Okay? So, 2 physically unique equilibrium points. Okay? And in one of the equilibrium points, the pendulum is looking exactly downwards with 0 angular velocity. And in the second one, the pendulum is looking upwards and it's vertical. Okay? So in one of the earlier examples, I have drawn an f function, and I have shown you the behavior of the system around the equilibrium points. Around one of the equilibrium points, the trajectories of the system would be converging towards the equilibrium point. And for the second equilibrium point, when I look at the trajectories around the equilibrium point, the trajectories were going away from the equilibrium points. Okay? And the pendulum system is actually a perfect example of that. Suppose that the pendulum is around the downward equilibrium point. Okay? And suppose that I make it with an external disturbance deviate from this equilibrium point just slightly. Okay? Then what is going to happen? There is friction in this system, and the pendulum will oscillate just a little bit, and then it is going to converge back to the equilibrium point. Okay? What about the upper or vertical equilibrium point, upward equilibrium point? If I make the pendulum deviate from that equilibrium point just a little bit, then the pendulum will fall back to the other equilibrium. So you see that the behaviors or perturbations around the equilibrium point of a nonlinear system can give quite different behaviors, can result in quite different trajectories. In the stability terms, we are going to call the upward equilibrium point of the pendulum as an unstable equilibrium point, and the downward equilibrium point of the pendulum as a stable equilibrium point. Okay? So, but the important thing here, in this lecture, we have seen the concept of an equilibrium point. And if we start the pendulum at an equilibrium point, the upward or downward, it doesn't matter. If we start it exactly at the equilibrium points, it's going to remain at that equilibrium point forever. It's never going to move, because there is no external disturbance, there is no input, there is nothing else. The system is autonomous, and if I start the system at an equilibrium point, it's going to remain there forever. So this was the investigation of a simple nonlinear system, how to investigate the equilibrium points. And I have also tried to give you the stability behavior around the equilibrium points, which we are going to see in much later parts of this course. In the next lecture, we are going to be looking at linear systems and what would be about their equilibrium points. Linear system is a very specific, is actually a very specific case of a nonlinear system. So I can actually look at the equilibrium points of a linear system as well. The same definition, just f is linear in that case. Okay? So we are going to look at the equilibrium points of linear systems, and then we are going to look at the equilibrium points of time invariant systems with different inputs. Okay? But this is going to be all for this third lecture. That's all. Thank you for watching. Bye-bye.